So we have with us Dr. Manish Pandey, Assistant Professor, Department of Civil Engineering, IIT Kharagpur. Now, before inviting him, I would like to give you a brief introduction of our eminent speaker. Dr. Manish Pandey is an assistant professor in the Department of Civil Engineering at Indian Institute of Technology, Kharagpur. His research interests span experimental hydraulics, sediment transport, river training works, hydraulic structure, and open channel flow dynamics. Dr. Pandey has authored more than 60 publications, including peer reviewed journal papers, book chapters, and conference proceedings. In recognition of his significant contribution to the field, he received the Best Reviewer Award for the Irrigation and Drainage Journal of American Society of Civil Engineering in 2023, as well as the Professor R.J. Gerde Young Researcher Award in the year 2024. Dr. Pandey is an associate editor for the ISS Journal of Hydraulic Engineering, Environmental Development and Sustainability, and the Journal of Applied Science and Engineering. He is also a member of the editorial team for the Journal of Applied Water Engineering and Research. Dr. Pandey has collaborated with prominent universities and research institutions, including the University of Glasgow, the University of Bradford, South East University in China, and National Chung Hsing University in Taiwan. It's our privilege to have you, sir, on this platform. I hope this session is going to be truly enriching for us as you have a vast experience in this field. So, without wasting time, I would like to invite Dr. Manish Pandey for the session of day 4.
Thank you, Ankur. Thank you
And
for
before,
inviting me.
yes, sir, before starting, I will do one thing. I will just mute all the participant, so you can then unmute yourself so that there will be no disturbance.
Uh, Thank you, Ankur, for introducing me,
Okay, sir.
and thank you for organizing this wonderful ATAL workshop and inviting me to deliver one lecture. So, my today's talk title will be Water-related disaster challenges and opportunities. So, basically, I will cover this water and sediment related hazards. Basically, what you will see in the river hydraulics. I will not go towards to the flood related or cloud burst related or mainly urban flood related hazards. I will basically go for the sediment and river hydraulics related hazards because these are very important things and always responsible for the failure of river structures, dams, reservoirs, hydraulic structures, irrigation structures, canal, and other such structures. So first, what is this disaster? So there is no single definition, as you know. So when at least 10 people died or killed, or 100 or more are affected, or appeal for international assistance at the time we require. So a disaster is an event that occurs in most cases suddenly and unexpectedly, causing simple disturbances to people, objects, and environment, resulting in loss of life, property, and health of the population. So as per the UN, United Nations, a disaster is serious disruption of the functioning of society of community causes widespread human materials or environmental loss which exceeds the capacity of the affected society to cope without external intervention. So that Sussman 1990 he defined that interface between an extreme physical environment and a vulnerable human population. Similarly, Anderson 1992 he defined temporary event triggered by natural hazard that overwhelm local response capacity and seriously affect social and economic development of the region. So as under the disaster there are several type of disaster. I'm only covering water related disaster, and under the water related disaster I will try to cover river and sediment transport related disaster, when disaster or hazards will occur because of the excess sediment transport or excess river discharge. So that basically these causes of water disasters are you can categorize into different categories such as extreme climatic events such as floods, drought, and tropical cyclones. So nowadays, due to the your climatic change and climate condition and climate change scenario, sometimes we are getting a huge rainfall. That rainfall intensity will be high. Suppose your annual rainfall is same, but you are getting this average rainfall for a very short duration. Suppose if you will compare this data, this 4 5 year data with the last 50-year rainfall data, you will find between July to August period, you are getting this complete annual rainfall. Suppose your in your area this annual rainfall is 1200 mm. So you will see that 90% of this limit or 100% data, 100% annual rainfall you are getting in between that, between July to August or July to September, within 2 3 months. So it means your rain is very intensive that time. So at that time, easily you can get floods, urban floods, or this cloud burst events. And similarly, if we are getting this annual rainfall for a small duration or in a very in a 3 4 months, so it means other during the other season or other months we will get drought condition. Okay, and then other causes are heavy and prolonged rainfall, flood, and depleted your rainfall, droughts, and change in climate that result into change on the mean frequency and intensity. As I told, we are getting main rainfall within 3 4 months or annual rainfall within 3 4 months. It means our intensity and the frequency are very high. So now, what are the challenges for the water-related hazards? So water-related disasters pose both direct impacts, maybe we can say damage to buildings or infrastructure, crop, and other infrastructure like your hydraulic structures, river training structures, irrigation structure, and as well as loss of life and property. So whenever you will get disaster, loss of life, and with this loss of life, property damage is also there. And indirect impacts, like for example loss in productivity. Suppose in Uttarakhand region in 2013, that Kedarnath disaster was there, natural disaster was there. So Uttarakhand was the growing state. Okay, this was the somehow newest state, maybe 27 or 28th state. So that time, Uttarakhand was going very well. But because of this disaster, that Kedarnath disaster, Uttarakhand's productivity was reduced because now all fund they diverted to the Kedarnath side, because this was a very huge disaster and it covered around 400 300 400 kilometer area from Kedarnath to up to Saharanpur Roorkee area. So up to this, they were trying to provide some maintenance works or river training maintenance work, infrastructure maintenance work. So productivity automatically will reduce because funds were diverting to the Kedarnath disaster side. And then increase the investment risk and obligation and human health impact. So also whenever this disaster will occur, maybe after every flood event, after every monsoon year, monsoon period, if you will see, there are so many diseases like dengue, malaria, and other diseases are also there. So health will definitely be affected because of this natural or man-made disasters. So the increase in economical cost and toll of disasters should be significant incentive for governments and charitable organizations to focus more attention on preparedness, prevention, and addressing the root causes of the vulnerability. So, what are the opportunities under this section? So, meeting the challenges associated with the water-related disaster requires investment in and implementation of good disaster risk reduction. So, how we can predict such disasters? So, nowadays, Hudhud recently one cyclone came to the near this from Andaman to the West Bengal, Odisha side. So previously they predicted that IMD predicted this thing and they prepared their things. They completely close all the government, private, and other organizations. They completely shut down the trains and the airways and roadways. So At that time, there were only very less deaths occurred here. So because of this early warning system, similarly, we can predict this earthquake by providing the early warning system. We can also predict our floods, urban floods, and sediment hazards. And despite improvements in prevention efforts, scaling these up to meet current and future needs remains a central challenges. So here you can see there are from this different photographs. In the first figure, you can see there is a lake surface before outburst. So sometimes you have must heard this thing in the news and newspaper. So there are some glacier burst and then glacier lake will fall down and huge disaster. So this in the D figure that is happened because of the one glacier lake in the upstream side. Similarly for the Kedarnath disaster also this happened, and here also is sudden this lake water will come to the downstream side, excess sediment transport, because at that time huge discharge or cloudburst event also you can tell. So huge discharge if come, so these big boulders will also travel with the flow velocity, and once these big boulders and the coarser material will move with the with the flowing water, and it will strike to the dam or any other infrastructure, it can easily collapse the hydraulic structure. So this uh, under constructed this dam was collapsed because of the excess debris and then coarser material with the flowing water. Similarly, this such scenario you have already observed in the hilly areas. In the hilly areas, one side there is uh, there is a river, and the one bank of the river you can see one mountain, and other side you can see some state highway or national highway, or some houses, villages are also located near the bank of the river. So what will happen? Some excess water, suppose this river is a perennial river, and every time it is getting Q discharge throughout year. But during the monsoon time, automatically discharge will increase. But if it will increase with the threshold limit, it can easily, suppose this is in the, if you will focus on C figure here, if this sediment will erode from the river banks, what will happen? This portion will be weakened, and all these houses will be easily collapsed. So such scenario you can see in the hilly area. Similarly, here you can see there is a very beautiful hotel located near the river bank in Manali. So here you can see just because of the failure of the river bank. Okay, so if you will construct your house as per the Vastu, so in the Vastu, they always suggest from the river bank, you just choose at least 500-meter distance, and then you start your house construction or hotel construction, whatever you want. But nowadays, just because of the tourism and beautification, they are just constructing the houses and hotels just near the rivers. So river can change their path anytime because of the because this river flows under the gravitational force, and wherever it will get the slope, this will move in that direction, and it will automatically shift either in the right side or left side. So if this is shifting in this side, it means it is getting erosion. Rivers are always sediment hungry. They will always erode. They will always responsible for the sediment erosion. So first that sediment erosion will start from the river bank from the bottom, and gradually it will increase, and after one time it will completely shut down, because this hotel, this is 5 floor hotel, so it has some dead load, so it will automatically collapse. Similarly, this is in the Nainital region, Nainital district near Haldwani. There is one between Haldwani and Kadgonam, there is one place, Rani Bagh, just after Kadgodam. So in this, this is your river, that river Gola, and here this is your national highway. So first that erosion started from this side, and after that it gradually increased, and there is a huge heavy vehicles are there, buses, trucks, and small vehicles are also there because this is your national highway. So because of the combined effect, this road is completely collapsed. So now how we can prevent such structure? So we have to provide some river training works. If we are constructing our hotels, house or infrastructure just near the river bank, so we have to provide proper river training works like spurs, like your groins, like your geosynthetic materials, like retaining walls near the river bank, so that this river training work will divert water in the opposite direction. So it will try to make its own path in other direction, and this structure, this infrastructure can easily prevent or can easily stable. So for both the structures, there is one is our road structure, road infrastructure, and another one is our this hotel industry or hotel structure, I can say. So for both the things, we have to provide proper river training works, and then we can think how we can prevent our these infrastructure, which are mainly important for your nation's growth. Now, in the coastal regions also, this is your coastal region, that water-related hazards are not only applicable for hilly streams, these are applicable for anywhere, wherever you are getting flowing water. So here in the near the coastal area, we are dealing with this uniform and with fine sediment, and there are huge waves. So every time these waves will strike to the shoreline or your infrastructure or your road infrastructure or your any buildings, hotels. So at that time, the shoreline we have to protect. So if we will not protect, such kind of failure we can see. So here other type of the protection work we have to provide some coarser material. You can see near the beaches, you will find some trapezoidal kind of cement, big cement structures are there. So this will break the this wave energy, and once you will reduce the wave energy, your erosion will also reduce. So this is the a series of check dams in the hilly streams. Hilly streams you can categorize with the steep slope. Hilly stream basically deals with the steep slope and coarser material. And in the coarser material and the hilly stream in the steep slope, you will get a huge velocity, high turbulence and turbulence intensity. So movement, boulder movement will be more. So for reducing the energy and collecting the water, they constructed a series of check dams. But the disadvantage of these check dams, every time it will choke after every monsoon period, because in these steep slopes we have high sediment rate, high sediment transport rate, and every time these sediment will struck near the upstream of the dam. So after every flood event or after every monsoon time, we have to remove these sediments. But what will happen if we will not consider this boulder load or sediment load for designing these check dams? So if we will get there is one water pressure, hydrostatic water pressure, as well as we have some silt load, or we can say this sediment load. This will also impact on the dam. So if we are not considering this sediment load, so this hydraulic structure can easily fail. And what will happen? This much sediment will move with the flowing water, and it will again responsible for the water related disaster at the downstream side. So this is the another case of the water related disaster. So now why this water and hydraulic structure and sediment transport related hazards basically we get in the rivers or in the natural streams? So suppose there are two examples. This is your natural river, this is also natural river, but in the first figure we don't have any obstacle or man-made hydraulic structure, but in the second figure we have one hydraulic structure. So this will basically we don't have any obstacle, any disturbance at the at the left hand side or right hand side. There is no highway infrastructure, and some houses or hotels are there, or some small villages there, but too far from this bank. Okay, and from this is upstream, this is downstream. So if you will obstruct or if you will construct any hydraulic structure here, at that time what will happen? Suppose after some times we constructed this bridge for connecting this village to this village. Suppose both the side we have some villages, and now connectivity is the major issue. So how we will connect? We have to construct a bridge. We have to provide some infrastructure for connecting one village to another village. So what we will do, we will construct a hydraulic structure. And now if you will see, previously its width was B. Now you can see, now we are changing its width because of these obstacles. Suppose the width of this river is around 20 meter, and we are constructing 1, 2, 3, 4, 5, 6 piers, and every pier's height width is 0.5 meter. So around 3 meter we are reducing. So we are playing with the nature. So now once you will play with the nature, nature will also play with you, because previously it was flowing uniformly. So now what is happening here? You can see, I cannot zoom in, because if you will observe here, a huge velocity or turbulence is there. And once turbulence and velocity will be changed, so sediment transport will also occur from this side. And once you are getting sediment transport in the flowing water, what will happen? This sediment will also move with the flowing water at the in the downstream side. And suppose in the downstream side, maybe after 10 km we have some reservoir, or maybe we have some weir or some any other hydraulic structure. So this will also obstruct, or this will also reduce its uh, capacity, reservoirs capacity. Reservoir basically we construct for collecting, for storage purpose, for collecting water, or then we can use this reservoir water for different things, maybe for hydropower, maybe for irrigation, maybe for domestic point of view, maybe for some fishery or some other point of view. But once the reservoir's capacity, because now you have constructed, you have changed the hydraulics of this river. Previously discharge will be same, because there is no loss, but its velocity at that time, suppose here we have constructed this bridge, this is your bridge. Now suppose here your velocity was v, because discharge is same, now area is changed, so velocity will change. And once velocity will change, your turbulence characteristics will also change. And you know velocity is the 3D function, so vector function. So it has three-dimensional components, in one in flowing direction, one in the downward direction, and another one in the transverse direction. So three components. So easily that vortex can form. So once that primary vortex and horseshoe vortex at upstream side will form, scour and erosion processes will start, and at the downstream side wake vortices will start, and this flowing water, flowing sediment, flowing water will also transport carrying the sediment. And suppose this flowing river, in the flowing river you are using some water related vehicles, and at the downstream, maybe after 1 km or after 500 meter, if this sediment will deposit it, so navigation height will also reduced. It will also influence the your navigation height. So different type of changes you can see in the rivers. So changes in the velocity profile leads to change in the sediment transport capacity, and usually cause of local erosion and scour of the river bed. So this scour and erosion mainly responsible for the failure of hydraulic structure. So as per one report which is provided by the uh, US government and New Zealand government in 2005, that 90%, 70 to 90%, 70% bridges in New Zealand were failed because of the excess sediment transport. And in US, 90%, this number was 90%. So every time bridges are not getting failed because of the earthquake or because of the excess load. So these bridges are getting failed because of the excess erosion and scour, especially for flowing rivers where we have high discharge, high sediment transport. So now Lin et al. 2024, they studied 36 damaged bridges and stated that the possible damages and scar characteristics mainly depend on the climatic and geological changes, which influences the erosion and deposition processes in the natural stream. And in 1993, around 20 bridges were failed due to the bridge element scour. Bridge element means there are different columns and different different piers and the abutment. So these are mainly responsible for the failure of your bridges, and around approximately 20 million US dollar in the coastal regions they lost because of the failure of their bridge infrastructure. So we also reported in 2011 that Belgaum, Odisha bridge was washed out because of the unpredicted scour around the bridge pier. So around 60% of the bridge piers hazards caused by the erosion and sediment transport. That was reported by the Legacy et al. 2007, and this they reported for the UK bridges. So now how you will follow this hydraulic design principle, so you can prevent your hydraulic structures, and you can you can safely design your bridges and other hydraulic structures. So basically this thing will depend on your flow parameters means your river discharge or flow depth and the velocity of river, and then sediment properties, what kind of sediment is there. So maybe sediment can be uniform sediment, non-uniform sediment, coarser sediment, maybe cohesive sediment, non-cohesive sediment, and structure intervention. So basically that sediment property, if you are dealing with the hilly streams, in the hilly stream, that flow rate, that flow velocity will be high and sediment will be coarser. And basically you will find the non-uniform sediment, different type of sediment. You will get this gravel bed, you can get the maybe fine sediment, and you can get some boulders, and you can get some sand also. So that is different mixture of the sediment. And if you are dealing with the plain areas, so there you will get the uniform sediment with fine sands, and structure intervention, how this water and sediment is interacting with the structure. Suppose this, you are providing different shape of the pier. Suppose you are providing circular shape or oblong shape or maybe rectangular shape. So at that time, how your pressure drag and the skin drag will influence its efficiency, or it will change the scour rate. So first we have to identify the scour problem. Suppose you have identified some river bank erosion or pier scour. After that, there are two ways. One, you can go for with the physical river modeling, and another one, you can go with the mathematical modeling. So for the mathematical modeling, we have sediment transport equation, different sediment transport equation. We have uh, unsteady flow, because basically in the rivers you can find the unsteady flow just near the hydraulic structure. And on the physical river model, you have to scale down. Okay, suppose you are dealing with the one kilometer wide and around 20 kilometer long reach, and in between you are constructing some bridge with 10 number of piers, so you will scale down. So basically we'll go with the distorted model. And then one important thing, how you will scale down the sediment. So suppose you are dealing with the coarser material, so up to 0.7 mm you can scale down as per the literature, because after 0.7 mm, if you will scale down, that cohesive forces will comes into the picture. And also this below 7.7 mm, your sediment will be ripple forming sediment. So several ripples will form, ripples and dune. So up to 0.7, suppose you are dealing with this 70 mm 7 centimeter particle size, you can take consider 1:10, 1:10, and up to 0.7 you can go. But after beyond this, you cannot go because ripples effect will come. And if you will consider 1:100 or 1:1000 for 7 centimeter or 70 particle, so cohesive forces or cohesive effect will come. Because for in river hydraulics, if you are dealing with the coarser material, your parameters, influencing parameters will be completely different. If you are dealing with the non-cohesive parameter, your influencing parameter will be different. After that, you will go for the dimensionless analysis. So dimension analysis you can conduct using the Buckingham's pi theorem, and then you will provide some empirical relations. Once you will provide any empirical relation, after that you have to check this empirical empirical equations using the available field data. If you don't have available field data, you have to categorize your data into 30 and 70% for 30% for validation. And once you will verify your data with the field measurement of your previous experience, so after that only you can provide some design guidelines. So these are the hydraulic principle for designing any hydraulic structure, or for designing, or for initiating any river training box. So now this channel morphology, as I told, this open channel flow always occurred under the gravitational force, and river will make its own path. Wherever it will get slow, it will flow in this direction. But by providing the different hydraulic structure, we can push in the another direction. Water we can push in the another direction, and some up to some stretches we can prevent our river banks. So this channel bank morphology is under this channel morphology, a meandering channel. We have already we have heard, and this channel meandering channel can give the right balance between slope, velocity, and sediment transportability. And meanders tend to migrate downstream with time. So time to time, if you will see, the S curve is like this. Maybe after some time, this S curve will be completely changed. Maybe like this. So maybe like this, because this sediment will go in this direction and this sediment will go. This is reverse tendency. Time to time it will flow. This is very long time process, but maybe after some time you can get this scenario. So intervention in one location can cause effect the another also, because if the this deposited sediment is more, here you have deposited sediment, if this is more, it will also try to push in this direction. It will responsible to for one force in the another direction, and because of this, this sediment will also move with the flowing direction, maybe like this, maybe like this, and it will deposit. And this sedimentation zone will be this side, and scour zone will be another side. And sand and gravel extraction can upset the morphology balances. So now aggradation and retrogression. So in aggregate, maybe your level is increasing, and retrogress means fall. Maybe scour and erosion you are getting. So a natural bed has overall balance between slope and sediment transport in this, in a regime or in an alluvial channel, we can say, which is an overall average of the flood of various sizes. So however, the major flood move much more material than the equivalent volume of small floods. So engineer, basically river engineers or water resources engineers, so they can interfere with the natural movement of the sediment. So now this example of the retrogression. So in the first uh, point, you can see this is your flow direction. Here you have an original stream bed. Now you have constructed one hydraulic structure. Maybe this is weir, and then once you will construct weir, so every time the flowing water, there is some sediment is there. So sediment is deposited upstream of the weir. Here sediment will deposit, and then clear water will move in this direction, and then sediment is picking up from the bed downstream of the weir, and then eventually your stream has new stable bed profile, because this will be your stream bed profile now, because there is some deposited sediment, and at the end here the sediment is carried over weirs and the downstream bed profile is restored, because we have captured complete sediment in the upstream side. So this can take many years. So now there is one case study for the bank shifting of the river Ganga in the downstream of the Bhagalpur Vikramshila Setu. So this study explores the extent of erosion using the ArcGIS for right bank erosion. During the past years, in many fluvial systems, this river hydraulics have been considerably affected by the human disruptions, as the land cover changes, urbanization happened, and the channelization dams we have constructed and diversion structures we have also constructed, and then sand mining, that is a major issue, the illegal sand mining, and government is allowing up to 2 meter we can do the sand mining, but that sand mafias, we can say, or sand contractors, they are going up to 10 meter, they are going up to 15 meter. So if you are interested to conduct to analyze such kind of study, simply 20-year data, 30-year data you can choose, and then using simply, if you don't have any images, using Google Earth also you can analyze, you can get some tentative idea for the larger rivers. Maybe for a smaller river you cannot get, because high resolution data you cannot get. So in the Bhagalpur, this is which is located in Bihar, has more than 30 lakh population with density closer to 1200 people per square kilometers. That is, this data is given by the Ministry of Home Affairs 2011. So River Ganga has been the lifeline of the Bhagalpur, Bihar. In fact, this is a lifeline for UP, Bihar, Uttarakhand, Kolkata. So which runs for around 2,500 kilometers through Haridwar, Kanpur, Allahabad, Varanasi, Patna, Bhagalpur, and Kolkata. So any alluvial river for such magnitude has problem of bank erosion. Attached with it, the Ganga is not an exceptional river for this study. So this study explores the extent of erosion using ArcGIS for the right bank erosion. So here you can see that bank erosion study which conducted using four different maps, in which two maps are from Google Earth 2003, that comparison of two images, that is 2003 and 2011, and two are from the USGS website. So that is for 1988 and 2006. So this Vikramshila Setu, Bhagalpur, Bihar, is around 4.5 kilometer or 4.4 kilometer long, and located at 135 kilometer downstream of your Mukamahi Bridge, and 190 kilometer downstream of the Gandhi Setu Bridge, Patna. So this Vikramshila Setu is the link between National Highway 80 and the right bank of the National Highway 31, and left bank. In the right bank downstream of Vikramshila Setu, there are two important schools, one DAV and DPS, and one engineering college, that BCE, and one agriculture university, BAU, and a national highway NH 80. And you can see in this figure. So here, just near the bank, one DAV, this is one engineering college, another engineering college, and this is your Vikramshila Setu. So this was the river bank line in October 2003. Now, can you imagine, this is shifted to this. So here, if you will see the width of the this your bridge around 4.3 or 4.4 kilometer, and this maximum shift is also around 4.4 kilometer. This happened only in 8 years. So now the basic data used in this study are digital satellite images which we got from the USGS, and two images we compared, one for 1988 and another one for the 2006. That image was taken with good visibility and being free of clouds. So area of interest was clipped using ADAS imaging for both images. Result of the this extracted layers from satellite image were transformed into the GIS layer in vector format. So change of river segments was detected by the superimposing data layer together by the order of raster vector and the vector vector. So bank line of this river was digitized considering two different years, 1988 and 2006 with vector save file. So the bank line of Ganga river is demarcated from east side of the imageries and channel changes in right bank of the river during the period 1998 and 2006 is estimated by this GIS tool through delineating the river bank lines and drawing polylines within bank line variation. So shifting of Ganga on river bank downstream of the Vikramshila Setu was confirmed using two different years, 2003 and 2011 Google Earth images. So now here you can see the river bank shift between 2003 and 2011. So up to this reach that rapidly your river is shifting, and here around 150 meter, here double just 373, and then up to 0.11 this point here this river was shifted around 1 kilometer, and it's a very huge. It means if suppose there is some village or some school or some infrastructure, all were gone just in 8 years. So from this study of the satellite image, we can say that 1998 and 2006 ArcGIS images. So we can found that there is significant amount of bank shifting occurred during this period, and in Bhagalpur, that which is your major city population residing on the right bank of the Ganga. So right bank of Ganga is main area of concern in this particular study. So image analysis clearly shows that the upstream of the Vikramshila Setu, right bank Ganga is almost intact, and downstream of Vikramshila Setu was getting more erosion than upstream. So the rate of erosion was found to be more in between 2003 and 2011 in comparison with 1988 and 2006. Why it is happening? Because after 2003 or 2006 there is a huge infrastructure development near the river bank. So we are just changing the hydraulics. We have just changed the hydraulics of rivers, and it is shifting in the right bank of the river, and we didn't provide any hydraulic structure to prevent the river banks. So contributing from the bridge cannot be ignored directly. So we have to provide some proper river training structure. So if you will see this 1998 line and this is 2006 line. So this is the comparison, and this is comparison between 2003 and 2011. So clear huge river bank shifting we can see. So now how you can prevent your hydraulic structure? So after analyzing this, maybe in 2014 and 15, the Bihar government irrigation department, they tried to prevent your river banks, and they tried to prevent farmers land and the other areas. So they provide different types of the spur dikes. In this is clearly visible. So such kind of arrangement they provided number of spurs. So whenever your flowing water will strike to the spur dike, it will try to divert in this direction, it will try to divert in this direction, divert in this direction, divert in this direction. Maybe if you will provide a very long spur dike, it will also affects this one. So maybe this will, you are providing spur dikes for preventing this bank, and you have provided a very long spur dike. So it is affecting the river bank stability of another bank. So up to 20%, the maximum length which you can provide, that can be maximum 20% of the river width. This will be your river width. This will be your river width, and this will be your length of dike. This can be 20% of the B, that is maximum. So similarly, if you will if you will change the shape of your hydraulic structure, you can prevent, you can reduce more hydraulic, more sediment transport rate. Here you can see that is T type of hydraulic structure. So T type of hydraulic structure, it will reduce more velocity, and by reducing more velocity, you can get the more sediment transport reduction near the river bank. And it can also divert more, and also sometimes if you want, if you have a huge velocity, so you can provide inclined spur dikes like this, so it will divert more water in the downstream side. And if if you have a locally available material, so you can provide this kind of the gabion structure of this type of the riprap near the river bank. So once you will provide the coarser material, what will happen for the coarser material, that water can also only move the finer sediments, but you have replaced very large boulders with the above the natural bed stream. So now it is very difficult to move this water for the particular discharge. So you can easily prevent this hydraulic, this river bank. And sometimes you can also see that we provide some sandbags. In the empty bags, we will fill some sands. We will fill with this locally available sand or sediment, and we will fix, and we can easily prevent this river bank. So now bank protection. So as I showed you some structures where the T type of spur dike or vertical wall spur dike. So this spur or spur dike encourage the sediment deposition, and these spur dikes may change the flow pattern and cause problems elsewhere, elsewhere wherever you want to reduce the sediment rate, or wherever you want to reduce the velocity by diverting your hydraulic structures. And revetment protects the banks from the erosion, and once you will reduce the erosion, so your 70% or 80% problem will be solved, because whenever you are getting the sediment transport, this is only responsible for the for your infrastructure failure, your hydraulic structure failure, or your deposition of sediment. Suppose you have one suppose you have one river, and here some this sediment, and once this is your pier, and this is your flow direction, this is your queue. So this pier and above this one bridge was there. So because of the change in change in area, the sediment, scour is there. So this sediment will also move, and at this side you have some dam. Okay, some reservoir or dam. So this sediment will completely filled here, because here velocity gradually where it flow, you can see, and here your velocity will be completely zero or negligible. So this sediment will settle down, and up to certain distance we can ignore this sediment. But once you are not achieving your aim, why you constructed this reservoir, because we want to store water, and we want to provide water in the for industry, for domestic, or for hydropower point of view. But if you are not getting sufficient water, if you are not able to fulfill the water demand through this reservoir, so after that you have to take some measures. So what you will do, you will try to remove this sediment. So here we have some undergated sluices, or maybe some dredging thing. But once, or maybe you can just open complete dam or complete barrage. Suppose you have barrage, so complete barrage you will open, and you will remove complete water. So at that time this sediment will also move, and again this will change the morphology maybe. And once the sediment will in the open area, it will deposited near the river, it will reduce the capacity of the flowing water. So during the monsoon time, easily water can enter into the villages or city side, because now sediment has captured the river's depth. So suppose previously up to 5 meters of water can flow, now 2 meters was captured by the sediment. So only 3 meters. So where 2 meter will go? It will go into the river, city side or below side, village side, which will always responsible for your hazard. This is always responsible for your hazard, flood hazards, or maybe other kind of hazards. So the ecosystem of this river, how you can make a healthy ecosystem by providing these river training structures or hydraulic structures or maybe spur dikes or other kind of things. So a healthy floodplain gives the water a space to spread out, this slow down, and river carries sediment and nutrients, and aquatic life flourishes when there is sufficient oxygen. So the vegetation cover prevents soil erosion and helps to regulate the water temperature. Sometimes we also provide some vegetation to reduce the erosion. So this will also increase the oxygen level and reduce the erosion rate. And floodplains can be rich and biologically diverse the environments and often support and abundance of the plants and birds. So floodplains are a take on and store excess water at the time of floods and releasing it slowly into the groundwater aquifers. If you are providing some floodplains, so groundwater recharge is also an important thing. So if you are fixing some floodplains, and it can store water during the time of flood, and after that it will infiltrate to the ground side and recharge the groundwater. So which eventually helps your recharge the rivers. So now, how you will provide this design criteria for the spurs? So that first thing is you can provide. Suppose this is your river. Again, this is your river, and this is your length of spur dike. This much. Suppose you are providing spur dike up to this length, so it will also influence this bank, but we don't want. We only want to prevent this river bank, because if again if it will you will get this river bank erosion from this side, again you have to prevent this river bank. So what you will do, you will provide another series of spur dike or another series of the river training work in the left side. So for this case, this thing will be not be economical. So we can provide only up to 20% of this channel width, the maximum. Below this, we can provide, but not more than 20% of the channel width. And the spacing. This spacing is a very important thing. So maybe around 3 to 4 times of this length. This spacing should not be 3 to 4 times. If you will provide 3 to 4 times, that excess is covered, because whenever you are providing some obstacle, you will also get some scour and erosion here, because ultimately we are changing the cross section. So now it will divert the water here, if you will find a high velocity as compared to the midline or center line. So once your velocity is increasing, it means its sediment transport capacity or initiating the sediment movement capacity will also increase. So this sediment will also go, but after some times, if you are getting excess sediment transport, this spur dike can also fail. And once this spur dike will fail, this load and the load of this soil erosion will move with the flowing water, and again it will responsible for the hydraulic structure. So suppose you are providing number of this spur dike, so effect of this spur dike should be there. If you are not getting effect of this spur dike, it means here you are getting suppose some x meter scouring, you will again get x meter scouring, because you are not getting any, that disturbance effect is completed, it finished. So some disturbance effect should be there, because this will be your safe zone. If you are providing, this is diverting like this, so it means this zone is very less velocity zone. That is why we are preventing our river bank, that river bank erosion is not occurring. But if again uniform. Suppose only up to this, again it will try to become uniform. Same flow streamlines you will get here. So it means same velocity, same is cover x here, x here. So suppose because flow rate is same and your sediment properties are same. So if it will fail, this will also fail, definitely fail. So this much area will wash out. So we have to provide that spacing designing we have to consider. So not more than 3 to 4 times of the spacing we can provide. So this is some design criteria for providing the spur dikes. So now the different types of the spur dike, as I told you, that vertical wall, these two type of the spur dike I showed you. Ah, these two type of the spur dikes I showed you in the figure. One is the vertical wall spur dike. This simply it will divert, and another one is T type. T type will reduce more velocity, and by reducing more velocity, it will prevent more your sediment transport capacity or erosion. And inclined and declined spur dikes are also there. And nowadays, some of trapezoidal spur dikes are also there, which we provide using the locally available material. So as per your suitability, as per your funds, we can plan what kind of spur dike we will see. And for more detail, you can follow this research paper. So from my side, I have completed this session. So now floor is open. If you have any query regarding sediment transport, regarding water and riverbank erosion related and scour and sediment transport related. So feel free, you can ask, you can unmute yourself and you can.
If there is any question, you can just ask questions. I have unmuted everyone. Now you can unmute you and you can ask the question, please. Even you can ask the question by putting the questions in the chat box.
Hello, good evening, sir.
Hello, good evening, Bhumika.
Sir, how do wetlands improve the structural integrity of riverbank during flood?
No, during the flood, if suppose if you will provide wetlands, so at that time it will reduce the velocity. Once your riverbank velocity will reduce, so at that time, suppose I have just you see there is a particle. This is your sediment particle, and for Q discharge or maybe some threshold velocity is needed to move this sediment. Okay, but here if you just see, so suppose for this from this figure you can understand. So suppose this is your particle and using UC up to UC or threshold velocity, if you will apply this velocity up to this, it will not move. And after increasing the velocity, it will try to move. Suppose we are assuming we are dealing with the more than UC. Our velocity is more than threshold velocity. So now every particle will move. So if you are dealing with the uniform sediment. So now if you are providing this vegetation here, okay, or wetland, so it will try to reduce its velocity. Okay, if you will see, if you will compare with the drag and lift force, these forces will be completely changed. So at that time, it will not cross the threshold velocity or critical velocity for sediment movement. So we can reduce the sediment transport capacity, and by reducing the sediment transport capacity, we can reduce the erosion rate.
Okay, sir. Okay. Thank you, sir. The session was really informative and beneficial for us. Thank you so much.
Thank you, Bhumi.
Any more? Any more questions?
Or if anytime if you want to contact me, or if you have any other question, you can feel free to contact me. Or if you want to visit our laboratory at IIT Kharagpur, you can approach me anytime. My email and contact number is given there. Ankur, you may share my email ID with them.
Okay, sir. Okay.
Okay, I can also share, I think in the first slide. This is my email ID and contact number.
Sir,
If you
even
will
I
share,
will be sharing the PPT. When you will provide the PPT, I will share them that
okay,
also.
oh, definitely,
So
definitely.
yeah, they will be having every detail from the PPT itself. No problem.
If they will face any difficulty or any clarification, they can feel free to contact me.
I guess this is over from the participants end also. So thank you, Manish sir.
Thank
Thank
you,
you for
Ankur.
accepting our invitation and thank you for being so informative session. It was so enriching session from your end because I can see in the chat box all the participants are just writing the feedback out there. And it is 8:30, around 8:40, and it is dinner time. And then also the 150 participants were added. So it is quite very good number. It means your session was very successful. So thank
Yeah,
you
it's a good
and
number. Yes,
congratulations
thank
to you.
you. Thank you, Ankur, for inviting me, for giving me this opportunity. So time to time, I will contact you. Okay.
Okay, sir.
Hopefully,
In
if
future, in
any,
future, I wish to have you in our college as well as for more
definitely,
sessions. If I
definitely.
am organizing any session, I'll just contact you, sir. Thank you so
Definitely,
much.
I will visit, and any student he or she is interested for PhD or MTech, they can approach me or they can visit our Department of Civil Engineering, IIT Kharagpur. I will
Okay, sir.
try to do my
Thank you.
best.
Thank you.
Okay, thank you. Thank you, one and all.
Good night, sir.
Good night. Bye bye.